It's a good time. So we're going to have a curve. And you're going to have a point, say, right here. You're going to have a point, second point, say, right there. And what we're going to figure out is the length of the curve from that first point to the second point. Yes, it is. Okay, so here's the thing. If you wanted to come up with a rough estimate for that length, how would you come up with a rough estimate for that length? You could do difference of x coordinates, or you could do the difference of y coordinates. Let's do a little better than that. You could make a triangle. Yeah, when in doubt, let's make triangles. You could just connect it with a straight line, right? You could draw the secant line, connect the two. So just to say use the same notation as what you'll see in your book, let's say that's point I, and to the left of point I is going to be one less, so we're going to say this is point I minus 1. If you wanted to find the distance between those two, you could draw just draw the secant line, exactly, a right triangle. So if this, my line isn't the best, we're going from there to there. This point right there, let's call it x sub I and y sub I. What point is this going to be? X sub I minus 1 and minus 1. Okay, so the notation you're going to see is this. You're going to see that if you ever see this, that just means the distance from p sub I minus 1 to p sub I. So between any two adjacent points on the curve.
Does it matter what order they are?
Not really. No, technically no, because distance is always going to be positive. But for notation purposes, usually less is to the left and more is to the right. And generally speaking, that applies to alphabetical order when you have tons and tons of variables in an expression. So what are we looking at here? If you want this distance, we're going to have, what's it going to be? Xi minus plus y sub y minus 1. What do you do to each of these? Square them, and then what do you take? Square root of all of them. Are you okay with that? Now, what's another way you can notarize this? What's x sub I minus x sub I minus 1? What's another way delta what? Usually delta x, okay? So what do you have here? We now have pi minus 1 pi equals delta x what? Squared plus what? Delta y squared. Okay. Now, you can't really do anything notationally yet. You can't do anything yet, right? Let's go back and look at that segment that we're looking at. Now, keep in mind, if we were going from another point to this point, what we're going to end up doing is chopping it up into even more divisions. We're going to add in like an infinite number of these points. But we're just looking at one segment. And what do we have that glues together lots and lots of segments? Integration. If we have a way to describe the general case for one of them, we can integrate across part of the domain and glue them all together. We're looking at one of the pieces in a general sense because this piece could represent any piece. Does that make sense, everybody? Okay, so here's a picture. Now, you get to here, and you're kind of stuck because there's not much you can do with that. There's no, what's the algebra 2 mistake that people make at this point? They just take the... Okay, you're in algebra 2 and you see this. What would be the algebra 2 big mistake that people make at this point? They just take the square root of each one. Is that correct? No. So please don't do that. Mean value theorem, you know that this exists. There's some x sub I star, and we know it's right about here, right? Something like that, just by this picture. That right there is going to be x sub I star. I don't really want to circle that, so this right here, we're going to call it x sub I star. And what do we know about x sub I star? By the mean value theorem, f prime at x sub I star is going to be equal to what? F of I minus x sub I minus 1 all over x sub I minus 1. You get to say a lot of complicated things. All you're writing is slope right here, correct? Yeah. What's another way to write? Instead of writing x sub I, what can we write instead? F of x sub I. We could replace that with what and what? Well, y sub I and... Oh, my blue line, man. I got to draw my blue line again. See if I can get it better this time. Not bad. Okay, so do you see this right here? You see this right here? What's another way to write this? That's delta y. Do you agree with that? Yeah. Okay, so we know that this, let me move this over a little bit, hold on. We know that this is equal to delta y over what? So what do we now know? We now know that delta y is equal to what? Delta x times what? F prime of And x sub I star is just one sample point between any arbitrary 2 points that are next to each other. So what are we going to do with that? Well, yeah, it is a specific point between. That is correct. But as you make it infinitely small, it narrows the scope down enough. So here's the point. What was our problem before? We had 2 variables. What can we do now? Change them. So we know now that distance from p sub I minus 1 to p sub I is going to be the square root of delta x plus delta x times f prime of I star squared again, right? Do you agree with that? Oh, another closed parentheses, thank you. And then squared. Okay, so another way to write that is delta x squared times 1 plus f prime of x sub I star, like this, right? Right? It is squared. Thank you very much. I did forget that. You're absolutely right. What can I pull out of the square root now? Delta x. So what do you end up with? You know that the distance from one point to the next is going to be delta x times 1 plus or 1 minus f prime of x sub I star squared. Plus. Thank you. That's just a type of plus. Exactly. So this right here, what's so nice about this? What's it written in terms of? Well, x. It's in terms of x. X. So what we now have, this represents the distance from one point to the next. How many points do we want to connect? A lot of them, right? So now we get to introduce the integral sign. We're going to glue all these together. Again, I'm doing this in a hand-waving way. This is the general structure. There's some notation conversations we would have to have if you're going to write down the technical proof. But right now, what does this tell you? This is the distance from one point to the next. So what do you think the final integral is going to be? What do you think the final cleaned up integral is going to be? If you wanted to clean this up, the distance from a to b, you're integrating from a to b. Well, no, we're not going from x sub I minus 1 to x sub I. That's only going from one point to the next. We're going from some arbitrary value to the next. And along the way, we're doing this at each individual little interval, right? So we're going from a to b of literally just the square root of 1 plus f of x squared, f prime of x squared, sorry, dx. What does that represent right there? This represents the distance from x equals a to x equals b of the curve what? What's the function? F of x. That's all. Usually you see this. There's one small change. This is in a brackets and they square it. Just to be, the first wandering in the dark step was to figure out that you need to do what trig substitution? Y equals 1/2 what? Tan theta. Why do you do that? Yeah, so what do you end up with? Is it 0 to 1 still?
1.107.
Wait, what? 1 d theta. Right. So now what do we have? We have secant times what? Secant theta times 1/2 secant squared theta d theta. And we're still, these are a problem, right? It's not 0 to 1. We like putting it in there, but is that, we shouldn't. And it's not good because what are those? What are they? They're y values, okay? I'm just saying that this is a y value, okay? Now it's okay because I've notarized it. Great. So we know that 1, we have y is equal to 1/2 tan theta. So we have 1 is equal to 1/2 tan theta. So what does tan theta equal? 2. So theta is equal to tan of 2. So where does that one go? So this one right here goes right there. And then you have 0 equals 1/2 tan of theta. So what do we end up with? Theta is equal to tan inverse of, which is what? So that's nice. And it's the theta value 2. So what do we now have? We now have the integral of what? 0 to 2 of what? 1/2 of secant theta d theta. So we know that if we have oh, I don't know why that jumped up. And it jumped pages too. That's weird. It's D block, right? And it's there. There must be some like gesture. So if we have u, we also need to find what? Du. So what's du going to be? Secant theta tan theta d theta, that's correct. And what is, we have dv, so what do we have to find? V, right? But luckily, we know what the integral of secant squared is, which is tan theta. Is that really super helpful? Yes, it's nice, because we wanted to pick something we could integrate. That's the whole point. So that's a sign that something is going right, at least, right? So now what do we, this is going to be equal to u times v minus what? The integral of v du. So what's u times v? Secant theta, tan theta, minus the integral of, well, hold on, it's v du, right? Tan theta, and du is, yeah, I understand, tan theta times what? D theta, like this, correct? Just to be 100% complete, what do we have on the outside? A 1/2, right? And it's all of this, correct? And we have to do this from 0 to what? Tan inverse of 2, and this is 0 to tan inverse of 2. Okay, so what we're going for now is, can this be completed? And is this something we can evaluate? Sure, this is something we can evaluate. Okay, let's just assume we can. We're really interested in this part, which is, to do this part, we have to answer the question, can this be integrated? Now, you wanted to group things together a little nicely, and what do you think, what's your hope? Your hope is that it is integrable, but what is it? It's tan squared theta, theta, d theta. And what's nice about this one?
Oh, tan squared.
Exactly. So what do you have here? 0 to tan inverse 2 of what? 1 plus times what? So we think that's nice, but what's the problem? Well, no, the integral of secant theta is not the problem. Okay, I'll ask you a different question. When I raise my voice to talk over you, try not to raise your voice to talk over me, okay? Kids, what brought us down this rabbit hole in the first place? What was the integral that took us down? What are we back to? Yay! Oh no. Okay, so do you remember that we did that weird trick before where we had the thing we didn't know, and we had the other thing we didn't know, and we turned it into two things we didn't know, and then all of a sudden we can divide one and it was okay, right? Remember, do you remember that, everybody? Remember that strange trick? Like, well, let's see if it'll work. I mean, I'm kind of worried at the moment. I'm worried. It'll be 0 tangent, well, let's 2 of secant theta d theta plus 0 to tan inverse of 2 of secant cube theta d theta. Keep in mind that this is being what? Subtracted, right? Correct? And what is this equal? This was the what? This was this thing right here. See this? See that, everybody? Ooh. Let's just start with 2, the integral from 0 to tan inverse of 2 of secant cube theta, right? D theta is equal to secant theta tan theta from 0 to tan inverse of 2 minus 0 to what? Tan inverse of 2 theta d theta. Well, the only nice thing about this is that if we can evaluate the right side, we're done. If we can evaluate the right side, we are done, right?
Yeah.
Do you agree? So now we just need to figure out how do we, on the right side. If we can evaluate everything over here, we're done because you just divide it by 2 and you're done, right? Okay. So what looks like the challenging bit of this? I think it's this right here. What about that? How do you integrate secant theta?
We already used our 50-50.
We did already use our 50-50. No, stop saying that. Every time you give me a 5-digit decimal in the middle of a problem, I die on the inside a little bit.
You should do it often, then.
You're from an imaginary country.
I know. I'm an android because you don't believe this, but
Okay, kids, I'm pretty sure we're on the right track here. I'm pretty sure we're okay. I'm going to check it. While I'm checking this, I'd like you to work on one of these problems, okay? Your enthusiasm is infectious, Devin. I know what I called you. His brother. Oh, really? Okay, kids, here you go. Work on this one while I try to clean up this last bit for you.
I think that was from
I'll check it. Work on this one right now. Okay, don't apologize. If it's better, it's better.
No, I'm sorry for misleading you. Is that wrong?
No, we're right. I'm not looking at your work yet. I'm looking at this way. No, we're right. It's just that is the sticking point. We absolutely got to the sticking point of this problem.
Wait, they left it as an eagle?
The green thing that we highlighted is the hardest part of this problem.
Oh, I thought.
No, they didn't use magic.
Maybe they did hope.
But they said they say, look at example 8 in 7.2, and then you get to example 8 in 7.2, and in example 8, 7.2, it says, look at Formula 1. So, you have to, it's like link hopping in Wikipedia. It's like, we have to go back, you go back, you go back.
Oh, wait,
And I don't know what I don't know what yours is, but it's not right.
I see mistake in mine.
Okay, not right.
Yeah.
Okay. I apologize. Making it too easy. Oh, apologize. Go to 3.
I give you the one for. How would you go about
Want me to tell you how to do it? You can work it out yourself.
Yeah.
This is from the category, Andrew, of pulling crap out of thin air. Okay. Here's a question for you. What's the only thing you can multiply something by and not change its value? Okay. Good job. How many different forms of 1 are there?
Too many.
Yes. So theoretically, how many different ways can you randomly make this thing look different but actually stay the same?
Too many.
Too many. I like that was good harmony right there. Okay, ready? This is what you have to multiply by. Is that it? Let me just make sure. Oh no. Hold on. That's close. Josh, Steven. Hey, what's up? Thank you. She is here. Campus Live, Tina at the end of the block. Okay. Yeah. Shot Heather show Campus Live. Did I say that right? Was that good? I said after class, go to Campus Live. No, he was laughing because it made sense, right? Here's your hint.
That makes a little bit.
That's good? Thank you. Okay, kids. Here's the random step. If you really want to know how to integrate this thing, you multiply this by secant x plus tangent x over secant x plus tan x, and then you can do it by use substitution.
So by breaking it up into substitution.
I should have called a friend.
Yep, should have phoned a friend. Well, you can, but you're going to end up with this rabbit hole if you do this, and then you look up this, and then you look up this, and then you're like, nah.
Will they give you questions like that?
No, not like this. No. But pieces of this could be there. Pieces of it could. Like, not this whole thing, but definitely pieces of it. Doubtful. That one is probably not really fair game because there's only one way to do it, and that's to pull a random multiplication out of thin air that you will not have seen unless you've seen it. Do you understand? It's not like
it's like you either know it or
1% is going to see that randomly, maybe, if they wander around in the dark for a long time. If someone's told it you, exactly, and you remember it. Well, even if you had seen it, are you always going to remember this random multiplication? No. Okay, kids, I will let you. You got to do this for homework right here. There you go. Well, you know what? I'll put it better than that. I know. And the 6 and 7 right here. There's your homework right there. You can start it right now. So you got to finish those 3. Here it is. I know. Oh, that's right. It's 55. So yeah, it is 55. Yeah. Okay. So actually, you know what? Don't worry about the other ones. You can do these for homework, but this is your homework right there.